Good afternoon, everyone. Hopefully you can hear me. So my name is Jennifer Keenahan. I am in the Civil Engineering Department at UCD. And I'm going to talk a little bit this afternoon about some of the work that I'm doing in the space of scour prediction and the offshore applications of this. So we've heard a little bit already today about the geohazards related to offshore wind, and particularly around erosion and deposition that can occur in these environments. And the only active offshore wind farm that we have to date at Arklow Bank has experienced these issues. And anything that we can do to mitigate these scour issues ahead of time is going to help de-risk the development of offshore wind. So we've heard quite a little bit already today about the vast amount of data that's available, that's being collected on an ongoing basis. And this is extremely valuable and very important. One of the challenges, however, is that this data represents a snapshot in time. And okay, we can have repeat surveys, which again is very valuable, but again, it's not a continuous collection of data. And equally, experimental work can be quite costly and sometimes infeasible. So what I'm going to talk a little bit about today is a method of computer modeling, computer simulations, that has a lot to offer in this space. So computational fluid dynamics, it's a little bit of a tongue twister, in essence is using computer modeling, where we're looking at the fluid behavior, the flow behavior in this environment, and we're capturing the dynamics, and so how things change with time and with space. So like I mentioned, we're using computers, the equations of motion of fluids, and quite a bit of coding and modeling. And part of the reason that this is quite important is that fluid flow is quite complex. It's not intuitive. It involves the interaction of many features. So intuitively, we'll understand that the seawater is a fluid. It flows. But equally, the individual sediment particles on a seabed can also be modeled as a flow. So if we take these two examples here on the screen, one on the left and the right, it's an identical set of plates lined up beside each other, but the flow is coming in the opposite direction. So B is the inverse of A. And the question is, in that grey zone between the two plates, will the flow behavior be the same? And this is the non-intuitive part, is that it won't. We'll get really high flow speeds in that red area on the left and much, much lower on the right. And this isn't intuitive, and this highlights the importance of looking at this dynamic fluid modeling. So taking this concept a little further, what we're looking at here is how we can use this modeling method, how we can use this analysis procedure to help us de-risk installations of offshore infrastructure. How we can understand the scour formation process that might occur around anchors, cables, turbine foundations, and so on. And just for a small bit of context, this really fits into the Earth and Society research area, and specifically the geohazards area of the iCRAG, of the iCRAG family of research. So specifically, the research I'm going to talk about today, the project work today, this has been funded by GSI as part of their short call program. And there's a team of work behind this. So I'd particularly like to highlight Mark, who you'll have heard from already today, and Gary, who's in the audience somewhere, who have been pivotal in developing this work. And we've also had some connections and collaborations with Ulster University, with ARUP and GDG along the way. So I would love to be able to get some information from a real turbine foundation in the Irish Sea, but I don't think anyone is going to build me one that I can then test. So what we've been doing is looking at shipwreck sites as a starting point. These have been here for tens and hundreds of years. Generally, they're avoided because of their cultural value, but they give us an enormous opportunity to validate the modelling methods that we're using. And there's quite a rich source of data available for these sites. So, for example, we started our work looking at the SS Powell. So this is about 10 kilometres off the east coast. It's in about 30 metres deep of water. The ship is orientated in a kind of a northeast to southwest direction. And there's some really excellent data available to us, and you will have heard others earlier from the Marine Institute and those linked with Infomar. There's some really excellent data available for this site, which is fantastic. So to summarise the modelling methodology, we've taken the digital elevation model, the rasters coming from the bathymetry data, specifically the 2019 data that was available, and we have used that as a representation of the surface profile, the bottom part of this box here that you're seeing on screen. And then we've also got the velocity information about what the sea is doing and the current information from the ROMS model at the Marine Institute. And this top image gives you a kind of an idea of the model, the mesh that we've created for this shipwreck, and then some of the outputs that we get and the flow behaviour around it. And this is the really exciting part of this work, because it's going to bring us to another level in being able to de-risk these sites. So this is a plan view now of flows coming from the two dominant directions. So this particular site is exposed, I suppose, tidally. So we tend to have a dominant flow from the northeast and then also a dominant flow from the southwest. And these show the velocities, the velocities that are experienced at this site at a particular elevation. And what we then did was we also looked at the bed shear stress at this site, and laid on top of that, in the red and black lines, those areas of erosion and deposition that we could detect from the bathymetry data. And there's quite a fantastic correlation there, which helps validate the modelling that we're doing. And so the outcomes from what we've got to so far is that we're developing this methodology, this workflow for this type of modelling, and validating it. And then when we compare that back to the bathymetry data, we're beginning to build a very powerful tool that will help us to identify those regions of the sea that are high risk and those that are lower risk. And I think it's a valuable point, reflecting back on the question earlier from the audience about, you know, we've got all of this data. What is the interpretation of this data, and how early does it come into that decision-making process? Does it come in before the auction or after the auction, and so on? So the goal, the long-term goal here, is to be able to produce risk maps, if you will, that will identify from an erosion and deposition and scour point of view, those regions that are suitable and those maybe that should be avoided. So in terms of the benefits of this work to consultants, to developers, to stakeholders, I think we're all concerned in the room today about the energy crisis that is potentially coming, and how we can decarbonise our electricity demand, and offshore wind is going to be pivotal in that space. And while this study primarily has looked at the shipwreck sites as being a starting point, the goal is that we'll move to geohazards more broadly, to cables, to anchors, and I know that floating offshore wind was mentioned a little bit earlier. That's on my to-do list as well. How we can bring in the mooring dynamics and the anchor and the trenching that might be likely to occur at the seabed. So quite a broad application to this type of work, and lots to do. And like I said, ultimately predicting the risk, quantifying the risk, and using that information to de-risk development in this space. So to date, we've been understanding the Scour process. We're going to expand on that work. We're particularly interested in looking at other shipwreck sites, for example. There's a whole pile of them. We started with the Powell, we've moved on to the SS Hare, and of course moving over to the West Coast also. There'll be different conditions there, of course. And how we can integrate those learnings from the shipwreck sites into the infrastructure that we want to and need to put on the seabed. And just the final thing to mention is that we've got, this is the UCD Civil Engineering Labs. We have a very large flume that has been sitting there idle for quite a long time, but I've just been able to secure a large investment to get it back up and running. So we've 100,000 euros going into that flume shortly, and we hope to use that along with the 3D printing facilities in the school to look at some lab scale experimental work in this space as well. So that brings me to the end of what I'm going to say. I'd be delighted to take any questions at any point. Thank you.
Any questions?
Yes, Mark.
So we've just done, Jennifer, in the context of the models, I mean the software, are you talking about something that can be used on a regular laptop, desktop, or is there kind of computing limits to the model itself?
Yeah, so there's quite a significant computational effort to these models. The software used is an open source software, which is fantastic, so there's no cost associated with that. But typically we've been using the Sonic cluster, which is at UCD, and also iCRAG, which is a large supercomputer available to Irish researchers to run these models. You know, on a good day, it'll run in 3 or 4 hours. If it's a more complex model and it's a bigger one, we could get up to days and weeks. But the fantastic thing is that there's minimal cost to us, the researchers. This infrastructure is there and it's available, which is great.
Hi, Jen. Thanks very much. I'm curious, how do you calculate the flow rates, the actual flow rates under the water, and how does it differ along different areas? So the equations underpinning the CFD modelling are the Navier-Stokes equations of motion. And so the outputs of the modelling gives us a measure of velocity at every point in the domain that we're modelling. Equally, it gives us values of pressure and temperature, and we can get bed shear stress and so on.
So that's the really powerful piece, is that we're not trying to put a load of sensors in the sea. Effectively, we are getting that information from the modelling. Now, I'm allergic to a black box like the next person. I like to have confidence in what's being done. And so a big part of this is the validation of the model, is checking the model against true data, real data, to have confidence that it's giving us what we believe to be correct. I hope that answers your question.